Universe Sandbox allows you to create sophisticated simulations on your home computer. But how? Hey everybody, and welcome to another video here on my channel Astronomy. I'm Thomas, and today I would love to talk about Universe Sandbox. Now, I created a small introduction 2 or 3 weeks ago, and today I would like to give you I wouldn't say an ultimate guide into Universe Sandbox, but let's say a medium-sized advanced guide to show you all the settings, all the possibilities you have with Universe Sandbox, and all the kind of simulations you can do. Of course, I cannot cover everything, but I try to get through all the menus and also change settings and change objects to show you what we can theoretically do with Universe Sandbox. And this video is a little bit long, so don't be frightened or so. I created some time markers here on this video, so you can click to the corresponding sections where you think, okay, this would be interesting, I would like to have a look, or not. Another thing is, of course, I'm not associated with the tool, so I'm not getting paid by it because this is not open source. You have to pay for that on Steam, but I like it and I would like to show you, and especially for those of you who are not into Python or programming or would like to do a lot of stuff in a very short time, Universe Sandbox is a very nice tool for educating yourself, but also a little bit for entertainment, because you can change things that are not changeable in the cosmos. And I would say, without further ado, let's switch to Universe Sandbox and enjoy the video. And please let me know if this kind of Universe Sandbox videos are interesting, or if you would like to see also some other stuff as well. Now, enough talking, let's switch to the, not coding part, but to the Universe Sandbox part. Okay, very well. Let's start with Universe Sandbox. And, well, this is the default window. Actually, the actual default window is the solar system, but I was thinking to start with an empty simulation, and we open first our solar system that is a default scenario in Universe Sandbox. Now we go here to the hamburger menu, and there are some options like new, open, guides, and so on. We go to open, and then we click to the solar system, and we have our solar system running. Now, all the menus here, we will I encourage you to explore everything. Today's video will be kind of large, but I would suggest not to exceed it too much by going through all the simulations. We will go through some settings maybe first, but yeah, and some certain scenarios we will build up, but not covering everything because that would be kind of much. Now, first, here in our simulations or predefined simulations, we have different categories like, yeah, of course, all, collisions, explosions, some systems, planets, constellations, and what have you. So just go through it and you will see interesting stuff to be discovered. Now, in our settings, we have, of course, here the standard graphic window settings as you have it in computer games, like, yeah, like renderings, rendering qualities, texture resolutions, filtering quality, and what have you. These things, of course, depend on your graphic cards and your entire setting. I would not go through all the settings because this is like, yeah, let's say the standard stuff to get a thing running. We are here to understand the simulation software itself. Now, we have here the solar system now running. We have here the sun in the center. We have Mercury, Venus, Earth, and Mars, Jupiter, Saturn, all different minor planets and also asteroids. We have here Juno. We have here Iris and Ceres. Pallas and Vesta is most likely also hiding somewhere. And if we scroll a little bit outside, we see also Uranus and Neptune. We have here Eris, Sedna, and also other objects that have a large orbit around the sun. And first of all is, of course, this is not real time, of course, this is kind of fast. We see here the current simulation speed is around 16.165 days per second. So yeah, kind of paced up a little bit. And here we have the time menu. Of course, we can make a simple hold or continue it and have a lot of different settings here for our time, like restarting the entire simulation, reversing time, or also some advanced time options, like for example, the date we would like to set, or we can also set the length and all the things. So we can simply click on start and have a dedicated simulation that is not running infinitely like this one. Now here, days per second, this of course depends highly on your computer power. You cannot go infinitely into or put infinite numbers there. Why? Well, we will get to this in a few seconds. Now this is a time menu, and the time menu, I would say, is kinda trivial. Or is it? Well, again, let's see later how things impact our simulation. Now the other menu here on the bottom, we have here the simulation part itself, where we see some statistics in this very small menu, like the number of objects and the number of objects that are attracting. So what does it mean? It means that 32 objects in this simulation have have a gravity and the others don't. Yeah? Of course, you may say, wait a second, every object in the solar system or in the universe has a gravitational attraction, and you're right, but this is like a so-called n-body problem. So n-body problem means that the solutions you see here, the movement, is not analytically solvable, but it is derived from numerical simulations. And the simulations become more and more complex or computational intensive the more objects you have to simulate. And if you have, of course, a lot of objects interacting with each other, you have more equations to solve than, let's say, with less objects. And if you compare the gravitational attraction of the Sun, Mercury, Earth, Jupiter, and the larger objects compared to a 100-meter size asteroid, well, for a solar system simulation, this gravitational pull of such an asteroid is kind of irrelevant. Yeah? So this is basically it. If you click on this, we have also some other statistics here as well. We have also the star count, which is apparently 1 in our simulation, because the background here, the Milky Way and so on, it's just some image being added or rendered, but it's not no physical meaning, let's say. We have here the mass and also some other physical parameters, like for example the complete momentum or so, but this is not important for now. We have here some further options as well. We can simply turn off the gravitational pull, and then we see what happens. We can do this in a moment. We can also enable or disable collisions. We'll talk about this later. And also fragmentation, because we can also simulate when two asteroids are colliding, then they're not simply exploding or vanishing, but smaller fragments are appearing. And this kind of simulations are theory very complex because they depend on a lot of physical parameters, like also some of course, like what kind of asteroid is it? Is it a solid object? Is it some maybe some accumulation of smaller objects? What are the properties? What is the density? Are there any cracks or so? But yeah, this is a very complex topic. So if you consider this fragmentation and collision simulation, they are a little bit more, let's say, simpler than compared to scientific papers. And you can also enable and disable the temperature simulation. But we will leave everything on. Maybe for the fun, we can just turn off the gravity, see what happens, and then turn it on again. It's kind of simple. We have here like our Earth and all the other planets that are revolving around the Sun. And of course, the vector of the velocity is always pointing to this direction, to the flight direction. And if we turn off the gravity, then they will simply continue flying linearly. And if we reactivate it, then they will find a new orbit around the Sun. So what happens? Let's see. We turn off the gravity, you see, as I said, straight lines. And if we reactivate it, well, if they're not too far away, like Mercury, probably shooting out of the solar system, then they are getting back into some kind of orbits. Now this looks kind of ugly, so I would suggest to restart the simulation, and we are back on track. Now simulation, or the menus here, they have also this small button here. We can extend it, and then we have more options. Let's call it the advanced simulation option. Now, the options here, you already saw them. We have here some menus like gravity between objects. We can turn it off. Also, self-gravity means that if we have like a pile of different objects, then they are sticking together. We can also turn it off and say, okay, we want to have only gravity between larger objects, or let's say only planets or so. And we can also adjust the gravitational constant. Like the gravitational constant is, you see here the equation, that the force is depending on the gravitational constant. So it's depending on the major mass, or one mass like the sun, and the other mass like Earth, yeah, divided by the root or the power of the distance to the power of 2 of the distance. So it's like m times, so mass 1 times mass 2 divided by the distance squared between these two objects. And to put things into perspective, we have also the gravitational constant as a multiplication factor in front of it. And you can imagine that if we increase this thing, then of course the gravitational forces between the objects get higher, and also the orbits will change as well. We can simply do this. Each menu is a drop-down menu like this one, where we can simply click between these 4 values, like only a tenth of it, 50%, or times 2, or times 10, or a small slider, or also write numbers in there. And then we can check what happens if we double the gravitational constant. Then of course the force is increasing between these objects. And you see here the orbits change slightly, like Mercury is now in a more elliptic orbit, as well as Earth and Venus. And then you can also compute and check what other parameters have changed, like, for example, apparently the eccentricity, the velocity, and what have you. Now, if we increase it even more and more, things become ridiculous. It's like simulating something that's not really existing, right? Because the gravitational constant is, as the name suggests, constant. Now, we can increase it, and at some point it looks a little bit funny though. Let's go back on track with only the number 1. And okay, now the simulation is breaking apart. So we are restarting again, and we will maybe not play around too much with all the stuff. So get back to simulation. The next thing is now the accuracy profile. As I said, the numerical simulations, this is like an n-body problem between all the different objects that are interacting with each other. And you can set for different profiles, like accurate, performance, or balanced. Like accurate means that there are more steps computed in between for a higher precision, and performance means that, well, you can probably add more objects with a lower accuracy. And then we've also some advanced options. And these advanced options are for those of you, maybe it's interesting for those of you who are maybe studying physics or numerical mathematics or what have you, where you can also, for example, set different integrators for solving the n-body problem. Now, I will not go too much into detail. Maybe the important thing is you can read here, like, for example, the Euler explicit thing. This is like the very first numerical integrator you will learn in the first semester in physics. You can solve n-body problem solutions, but very inaccurately. So with a few time steps, the whole system breaks apart, basically. It doesn't preserve certain values like energy not very well, so it's extremely unprecise. So I would suggest, if we do this, we can maybe see how this may affect our computation, if at all. For now we don't see it. We should maybe add more objects or so, maybe increase it over time. Then we see that maybe the orbits become a little bit unstable. You see Mercury already flying away. It's getting a little bit more chaotic. Mercury is doing strange things. Venus and Earth are becoming tandem partners here around the sun. And you get the idea that this thing is a little bit unstable. So it's not very suitable for long-term simulations. There's like nothing anymore inside. Mercury and Venus are disappearing, in Earth as well. So Euler explicit is something you shouldn't really choose. Maybe in my Python series we will use it to understand it from a mathematical point of view. Maybe could be an interesting project, but I would suggest to stay with these Hermite integrator, and the rest leave it as it is. Now I would suggest again to restart our simulation because we messed up everything. Welcome back to the year 2014. Now, menu back. Yeah, we have here also some performance metrics and also some settings for the collisions and fragment creation and so on. So I turned on everything basically. You have to check it with your computer. If you don't have the performance, then I would suggest to turn off maybe fragmentation or collisions. Then you can use more resources for the astrodynamical computations. If you would like to go more into collisions and see what's happening, maybe remove some objects and check for the collisions. It's up to you basically, right? Now we have here also the background temperature. The background temperature is something you may have heard about. Well, maybe the Planck satellite or so, like the microwave background of the cosmos. It's like the fingerprint of the Big Bang, and it's currently at here 2.7 Kelvin. When you go back in time with the cosmos shrinks and the temperature increases more and more and more. Maybe it's a topic for also a totally different video. I think also the Nobel Prize was given for this in the 50s or 60s, I think. But yeah, you can also play around with this value and see what really happens and cook the planets a little bit if you increase this number very, 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 very high values. Surface materials, this is really crazy because we have also possibility to change properties of planets and their material abundance and what have you. We will get into this as well. I just turned on everything, and that's basically it. So this is all for the simulation part. Now the center menu is the viewing part. It's also like, yeah, almost kind of self-explanatory because it's for the cosmetics a little bit. We can turn on and off the labels. I like to turn it on. The trails as well. The trails are quite helpful, but orbits can be a little bit noisy if you have a lot of objects. So I like to play around with the trails. Now the grid is the grid is like the grid of the ecliptic J2000 grid. Here in this case it's like in 2-dimension, but it doesn't really add up a lot of information. For me, it's a little bit chaotic. I like to do it more with, as you know, Python. So let's leave it, let's turn it off. If we add, of course, objects, then of course you have to consider the proper distances and so on. What's interesting is this, the visibility of the habitable zone. So the zone where water is liquid, and where liquid water is, life could emerge. And we can also turn it on here for our solar system. And you see the red zone, kind of hot, where Venus is almost there, and Mercury, of course. And then we have here the green zone with the higher probability of having a habitable planet. Surprisingly, Earth is there, but we have also Mars. However, Mars has no really thick atmosphere and no magnetic field and no water, so it's also kind of dead. But this is like, let's say, the area where we could put a planet there and do some terraforming. Now let's turn this off as well. And then, of course, camera setting and charts and so on. I don't like to show the charts now. Otherwise I have to restart again. But I would suggest to play around as well. And of course, we can also add velocity lines there. But I think I would like to also turn this ones off. Let me just increase it also here to the left side. Lightning, colors, object visibility, and so on. Yeah, these are just, as I said, a lot of cosmetics. Longitude, latitude lines for Earth, for example, we can turn it on and off again. I also left it here off, and also a lot of different other markers. This is not really that helpful now. I would put it here I would suggest to put it into the default settings. Also materials like iron, silicate, oxygen, and so on. You can basically modify anything. The next thing is, of course, the tooling. And now the question how I would like to do it, because I think before we go into the tools, because also we have here like the add button, which is basically also here, it can be kind of chaotic. I would suggest let's talk about it later, and let's have a look at some of our objects here, like for example, Earth. Now, if we click on the different objects, like whether it's Sun or the Earth or Venus or what have you, we have here the small menu. We have here the mass, which is given in Earth massage, which is surprisingly 1. We have the radius given in Earth radii, which is surprisingly 1. We have the average density, which is 5.5 grams per cubic centimeter. So this is like a value for a very stony planet. We can maybe compare it just in a second with other planets, gas planets maybe. We have here the average temperature, 6.95 degrees Celsius, and also the orbital velocity of around 30 kilometers per second. Now you see here also now the lines a little bit. This is like, these are the artifacts of this numerical simulation, as I just said it. So this is like an extrapolation, but the precise steps are computed in real time. Now I would suggest let's go maybe to Jupiter. Let's have a look here. We have 5.5 gram per cubic centimeter. Let's go to Jupiter, and we see Jupiter is less denser by around a factor of 3 or 4 with 1.99 gram per cubic centimeter. We go back to Saturn, it's 0.6, so it's even less denser. And we have here Uranus with 1.27, so also around like Jupiter, and Neptune a little bit denser. Now the rocky planets like Earth was 5.5, we have Venus with 5.2, and Mars also with almost 4. So these are like the very rocky planets, and it's these are like, let's call it average values. The values you will also see for asteroids, for example, here Hygeia, I don't know how to pronounce it, also with around 4, Ceres with almost 4, and also here Psyche with also around almost 4. Now, these are like something you can learn also from Universe Sandbox, like the physical parameters. They are coded pretty well. Let's go back to Earth and let's extend the menu. And here it's getting interesting. We have a lot of stuff. We can change the name. Well, it's not really interesting. But we can change the mass, we can change the radius, the density, we can change the temperature, the orbital or the speed, the orbital period, and also other settings like, for example, motional parameter, like the distance, and also the orbital parameters I talked in my Python videos, like, for example, the semi-major axis, pericenter, eccentricity, and so on. Let's change these values in a few seconds, also rotation and so on, like a lot of stuff we can change here. I would suggest let's play around with the eccentricity a little bit, and it's pretty funny. You can really change things in real time. Now, I would suggest to center the sun, go back to Earth, and we increase a little bit the speed so that we see directly an effect. And here on motion, we go now to, oh, where is it? On the very top. It is here, the eccentricity. We click on it, we see the menu popping up. The interesting thing also is we can plot also a graph for all the different values. So everywhere we have a graph, we can also plot it here. You see an eccentricity of around 0.0 is circular, so we have an almost circular orbit. And we can have also here like adding more objects. We can also determine what we like to have on the x-axis and y-axis. So it's pretty crazy. You can do a lot of stuff and be really scientific with this, which is really nice. Now the changes here and the eccentricity, they are very tiny, minimal changes. And of course, they are a mixture of actual effects like gravitational pull from Jupiter and also other objects, but also errors from the numerical simulations. You have also to take into account that these things happen. Looks pretty nice, I would say. Maybe before we change anything, let's play around here a little bit, we can have here the time pass. We can also, I don't know, the eccentricity versus the mass, probably a straight line. It's not really that cool. So the changing mass is maybe more interesting for a comet when you're simulating a comet, for example. But we can also add here another object, like for example Venus. So we select it, and well, it's not very scaling well now. Well, it's not very well scaled. Maybe we have to wait a little bit more or so, but yeah, unfortunately, it's not very good. Yeah, well, doesn't look very promising, I would say. You can see at least the values here, but yeah, let's leave it with Earth and then it's resetting again. Cool. Where is the eccentricity again? Yeah, there it is. Of course, we have the same menu as I showed you before, and now we can really change the values here by increasing it a little bit. Yeah, so a little bit plus, and then you see it's affecting only not much now. Let's go a little bit higher and higher, and you see already how the orbit is getting bigger and bigger and how it changes with the eccentricity. It's getting pretty interesting. You can now increase it, for example, up to Jupiter's orbit, like a so-called Jupiter family comet, like the comets like Churyumov-Gerasimenko that are being, let's say, manipulated by Jupiter, and then we can increase the time again. And then at some point we have close flybys with Jupiter, and this should also change the orbit a little bit. So it's a little bit crazy stuff you can generate. Oh, we have a close encounter, and you just saw how the orbit increased. So what we did now with Earth is what the comets are doing, or what Jupiter's doing with the comets, with the Jupiter family comets. It's pretty interesting. We can also make a dedicated video about Jupiter family comets. But yeah, as I said, you see sometimes some close encounter, and then Jupiter is altering the orbit of our Earth 2.0. Not very friendly to live on, I would think, but yeah, this is, I think, another task for us to restart the simulation. Good, let's go back to Earth. We did not cover all the menus yet. We can also have a look at the surface. Now this looks very bright and so on, but this is like the temperature distribution. And of course, this is not 100% realistic, right? It is kind of nice. The equations are also partially online. I'm amazed by the degree of detail, to be honest. Yeah, you can put the surface. We can also change things for the sea level. It's really crazy. And then we can also change, for example, the atmospheric the atmosphere percentage, the distribution of the gases, for example. Like, you know, we have like the climate change, of course, with all the carbon dioxide that we are emitting into the atmosphere. And we can, for example, simulate this as well. Like if we would double the CO2, what would happen? Of course, as I said, this is simplified simulations, right? But it gives you at least a good hint. So if we increase it, for example, by a factor of 2, yeah, we see like here, this like the temperature distribution. Nothing will change for now, but over time it will change. Yeah, so we can increase it and doubling it, and then you see slightly it's starting to increase more and more. So the highest temperatures are getting higher and higher. And as I said, of course, take everything with a grain of salt here. If you want to learn about climate change or so, then read the corresponding papers and the very highly sophisticated simulation in this regard. But hey, it gives you at least an idea, right? So 50 degrees Celsius is kind of hot, I would say. So we can increase it even more and more. And the funny thing is we can then also change, for example, nitrogen or water, and then also take a look here at the distribution of frozen water, of vaporized water, and so on, and change also the distributions here, which is pretty crazy. So I just vaporize all the water. We can do it again. And then you see like all the changes, what happens. You can play around with it. It's pretty fun. But I think doing dedicated simulation is something for an entire video here. I just want to show you the options you have. You can then stabilize the phases again and so on, and also change the sea level of the Earth's water and so on. You can even change the energy rate that is being added to the planet. Well, if you change the values of the sun, so you cannot really change it here. And also the atmosphere settings like pressure and the mass and the density and so on. So everything that has this small menu here is changeable. Everything else is, let's say, just being computed. Now, this is like the part we have here for our surface. Let's leave, 80 degrees. Well, let's leave this hell of Earth back, and we can go here to Mars, for example, where everything is way colder. We have here like the hottest temperature currently minus 50 degrees. And then we can also do some terraforming, right? So we could, for example, increase the oxygen levels. We can increase the carbon dioxide levels. So we can, for example, put it by a factor of 10 and then see what happens. It's, yeah, of course, there are a few magnitudes. It's very, very fast, but you already see the temperature increases on Mars. Now back to Earth. We can also change the composition of the planet itself, also from the other asteroids as well, and this is like totally insane. So you can change everything, right? Like what happens when we increase the density of the iron or so, then the mass increases and the total density increases, the gravitational pull increases. What kind of effects does it have on the atmosphere and so on? You can change and create planets that are not existing, or you can change the solar system into something that's not existing, which is pretty cool. And visuals, of course, is, yeah, cosmetics, let's say. The action item itself is also a little bit self-explanatory. We can replace it or delete the Earth, but we can also add moons to this planet, right? So we can also use this option here and add more moons, but I prefer to do it manually because you cannot really control it nicely here. But yeah, that's up to you. We have here also this open multiple data views. If we click on this, we see all the maps of Earth at once, like for example, the elevation, the gas pressure, the temperatures here, the normal nice aerial view, although some ice is missing. Because, well, the temperature is quite high, of course. And also the liquid water and so on, ice thickness. Well, currently no ice thickness here. So we have all the different maps in parallel, and then you can do some changes. Very well. Now we can go to the tools, because here we have the different things for creating, modifying, and some kind of powers. But I would go now directly to our planetscaping, because the planetscaping is exactly this, what we already did with Earth and also with Mars. So we have here now Earth in our menu. And what you can do now live is, for example, adding liquid water, for example. So you see here, you can add the liquid water and see, for example, where it's floating in, or where rivers are being created and so on. Now, the thing is, a lot of water is evaporating quickly because it's kind of hot on this planet now with 90 degrees. But this is what you can do. You can change the radius of the marker here and also the flow. And then you can, for example, go here and then add some water. So if you are living in a country and you're wondering, hey, where would the rivers be if we would have a water source, I don't know, somewhere in the mountains, and there are no water sources, you could theoretically create your small simulation and see what happens. We can also add ice here, but here it's not very effective because the planet is kind of hot, so it vanishes pretty quickly. And then we can also make the mountains bigger and so on, and then simulate, for example, a new mountain range. What would it have an effect on on the ocean and also on the temperature and so on. So as I said, a lot of stuff, really a lot of stuff. I'm so amazed by this, and I'm sorry if you're getting tired, but I'm totally into this stuff. It's it's really nice, I have to say. But let's go back from this planetscaping. I think you get the idea, I think. Now we can add objects as well. Let's see what we have, and we have basically everything. Yeah, we have like here all the objects. We have here the stars, we have here the planets, we have here moons, we have here minor objects. We have also some random objects like teapots, footballs, or also the Hubble Space Telescopes. We have even entire galaxies. For this, I would suggest to make an entire new simulation, and we can even add black holes in there, or also some rings like the Saturn rings and so on, and launch objects. Yeah, so for example, we could take a look at the sun. Yeah, so this is like, I would like to go to the center. Where is the sun? There it is. So we have here the sun, which is like the size. And we can, for example, if we add another sun, you can put it into a relation like, of course, this is another sun, so the same size by alpha tau. What is this about? Well, it's a huge star, I would say, and it would almost eat up the orbit of Mercury. So it's really these things put things into perspective, like how small our star is compared to others. Alpha Centauri A and B, you may have heard about them, our next neighboring solar system. But these stars, they are also, let's say, almost the same size, so pretty 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 decent stars. Now, Betelgeuse is a star in Orion, and it changes its luminosity all the time. And people think that it will explode soon. And soon means in astronomy somewhere between now and the next millions of years. So we really don't know. But we can click on Betelgeuse and see how large this star is, and this is ridiculous, right? I mean, it would eat up the entire inner part of the solar system. So let's not add this one, otherwise we create some chaos. And we have way more stars. So this is pretty cool, I would say. So you can add these objects, like for example, if we put again the second sun, we can put it here into orbit. But we can also put it into still position, so it would attract and probably collide with the sun, or also like a binary object, or we can also launch it, yeah, like shooting it into the solar system. If we put it here in a still, yeah, you saw it created some supernova. It was pretty fast, I would say, and it's like a small simulation, of a supernova, but yeah, well, I would say there's a lot of interpretation in this one. We can also reverse the time, or I would suggest let's restart it again. And we are back on track. Everything is calm again. Now, if we, what's really interesting is if you want to play around, we can add maybe a second Jupiter or so, because Jupiter has a high impact on the solar system. Because I would suggest to do the following. If you are, for example, if you look at the solar system, everything is rotating retrogradely. So they are, if you look from the top, anti-clockwise. Now we can, for example, remove Jupiter, which is at around 5 astronomical unions. Let's remove it. Au revoir. And we add another Jupiter. Where is Jupiter? Jupiter is here. We can maybe put it a little bit closer. Like where's Mars? There. Of course, a large gravitational impact on our solar system. But what's interesting is I would like to stay in the center of the sun here. Yeah. What's interesting is you can, for example, with Jupiter now, if you add new objects, you can reverse, for example, the inclination by 100 degrees. So it's now prograde, and this is making me crazy. And now you can, for example, increase the speed and see what happens if we would have a prograde larger object. Let's say it like this: if you do the simulation for a long time, it would create a lot of chaos in the solar system. So this is like, for example, one interesting idea to play around to see what happens if such a huge planet would revolve retrogradely in the solar system. Let's say it like this: in the long run, it wouldn't end well. starting again and going back to our tools. Now we have also here the Planetscaping, as I said, transforming, but I don't want to show everything. I always encourage you to play around. We have here, they also say like the like system management. We can increase the eccentricity of all objects, for example, at the same time, decrease it, or expanding the system, but these are just like fixed values for the entire system. So again, I would like to have everything back to normal, so I restarted yet another time. Good, so I think you got a good idea of all the things we have here in Universe Sandbox. And the idea is, or the art of using this tool is to get an idea what kind of simulation would be interesting, right? So the good thing is we have a lot of things here that are existing. Like what I also like is like the Milky Way and Andromeda galaxy collision, which is also a little bit different. I think these are not individual stars that are being computed, I presume. But yeah, you can see here there's the Milky Way and the Andromeda. And then we are computing here in mega years. Now, if we increase the speed, then we can also compute the collision, which is pretty fancy. But yeah, I don't know how precise this is, but yeah, at least it's nice to look at. And also, yeah, three-body problems. You can have a look at the three-body problems, for example. All the moons of Jupiter, for example, is also crazy simulation. So yeah, there you see all moons of Jupiter. Jupiter has a lot of moons, as you see. We see here the ones in the inner parts, the Galilean moons. We feel like around 1 hour per second. But if we go outside, we see the other objects. They all appear to be almost still, but of course, because of the time, we don't see now any larger movement. Supernova, we just saw it. These things are also being simulated in a way. But what's also interesting are these collision thingies. Like, for example, Earth and Moon collision, for example. We have like here, you can collide these things, and then, for example, what we can do is I would suggest to make a stop and restart it at, yeah, please restart. And making, okay, just making a halt, clicking on Earth, then you can go here to the surface temperature, for example. We can go here to the average temperature and the graph. So this is what I mean. You can plot a lot of stuff here, which is pretty fancy. Minimum, maximum temperature, no, let's leave it like this. I would suggest also to make it a little bit slower. Even slower, even slower. And then, yeah, you see like the average temperature increases because of all the heat that is being created here. We can also plot another thing. We could also add, or we can also change it and create another panel. Here we have the temperature, and here we have, for example, the time passed and the mass. As I said before, we have here the mass, and I think it should change as well because of the moon that was crashing, creating the fragments leaving, but some fragments are re-entering Earth, of course. I don't know why this is. We have this zigzag here. It is a little bit strange. We saw here in the beginning we lost some mass. And yeah, looks kind of frightening. Here we have a small fragment. Nice. Again, it's a very simplified simulation, of course. Oh, we got some mass back, probably because of the fragments. Maybe these are also some artifacts of the simulation. And we've also our temperature. Very cozy, 1000 degrees Celsius. So pretty nice temperature for the winter. And we see it's now being bombarded by all the fragments. Now, as I said, the question is how precise is the simulation? Yeah, you have to decide it a little bit for yourself. But I would say that it has a nice educational character, but it's not 100% precise. Of course, what does it mean 100% precise? I don't want to discourage you. I use it also for my videos, Python videos, sometimes to understand things a little bit better. But I think my personal assumption is that you couldn't write a scientific paper now about collision physics or so, right? But again, it's very mighty, powerful tool and gives very good idea of these things. Oh, we see the mass loss is going up again, but yeah, only very tiny fractions probably. So yeah, we can increase the time also, see what happens. Some mass is flying away. The temperature is also getting a maximum value somehow. If we increase the time a little bit more, maybe it will cool down again. But whoa, this will take some time, I think, to cool down. But all life on Earth would be lost. So let's be thankful that our moon is not doing crazy stuff. I think that's pretty good. Our fragment, where is our fragment? Oh, there. It just flew into the cosmos and never coming back. Now, well, this is what I wanted to show you about Universe Sandbox, some kind of small, not small, but medium-sized introduction with all the options you have. I encourage you to use the different default settings here and play around. You can create a lot of nice things. There are the limitations, of course, but after all, it's pretty amazing. I hope you learned something. I hope this long video creates some kind of value for you, gives you an idea how these tools work and look like. I will set some time markers. I hope this is something you liked. And until then, I would suggest thanks for watching and see you next time.